Hi friends, welcome to my channel. Making associative learning competitive and making competitive learning associative. This sounds kind of philosophical, right? These are actually the two key ideas behind the 1991 classic, where a mixture of experts were officially born. Today, I will unpack what this really means and how it was applied to improve mixture of experts. I will also talk about how we can apply these principles, not only improving the model, but improving ourselves. So here's our agenda today. We'll first talk about associative learning and what is competitive learning, and we'll do a comparison with these two kinds of learning. After that, we'll talk about what is mixture of experts. And then we'll talk about, in the 99 paper, how it improved mixture of experts by making associative learning competitive and making competitive learning associative. Lastly, we'll recap and understand how this can be applied to not only machine learning, but also our life and career. Let's get started. Let's talk about associative learning versus competitive learning. Associative learning maps input directly to outputs. You can think about them as a standard neural network that processes information collaboratively across all its neurons to produce a result. Every part of the network contributes to the final output. It is inherently collaborative. For competitive learning, on the other hand, it assumes that you have multiple subnetworks, which are experts here, through a stochastic process here, which is gating network. You select the one expert that is most likely to give you the desired output. Only the winners contribute to the result. It is inherently selective. Another aspect to think about this is that associative learning works like an encoder. It transforms input to output through a deterministic process, whereas competitive learning works like a decoder and generator. It is a stochastic generator that knows the distribution of outputs and select based on probability. In competitive learning, we can have hard competition. Only an expert with the highest probability contributes. We also can have soft competition. In soft competition, the probability is modified so multiple experts can contribute, but still favoring the strongest. Here's a quick summary for the comparison. There are 4 dimensions we differentiate associative learning and competitive learning. For the core task, associative learning maps input to output deterministically, whereas competitive learning is selectively choose one subnetwork to produce output. A typical model for associative learning, you can think about standard regression or classification network, whereas competitive learning, you can think about k-means or a mixture of Gaussian. In associative learning, all subcomponents collaborate, whereas in competitive learning, only one or few strongest subnetworks will represent the output. The analogy here is that associative learning can be think about as encoder, and in competitive learning can be think of decoder or generator. We just talked about associative learning and competitive learning. How are they related with mixture of experts? To understand that, we need to understand what is mixture of experts first. The insight comes from recognizing that complex tasks often involve multiple subtasks that are different based on the input. Mixture of experts address this by creating multiple expert subnetworks. So they each are independent neural networks and specialized for different subtasks. Also, mixture of experts have a gating network. It routes each input example to the appropriate expert. This is inspired by how we solve problems in real life. When facing a complex task, we often break it down and delegate subtasks to specialists with relevant expertise. Think about divide and conquer. The genius of MOE is that it combines the good things about both worlds. It has the specialization advantage of competitive networks. It also maintains the input and output mapping capabilities of associative networks. So how did the paper make associative learning competitive? The original 1991 MOE paper made a crucial innovation in how it approached the error function, what we now call the loss function. The standard approach is associative. As you can see here, it uses error function of the desired output minus a combination of all the output from the experts. So here, E is error, Pi is the probability assigned by the gating network. This function treats learning as collaborative because all the experts contribute proportionally to the final output. The paper improved this by introducing a competitive error function. So as you can see here, instead of comparing the desired output with the combination of all the experts' output, in this new error function, it compares the difference between the desired output with each individual expert output. So the reason why it is competitive is that instead of asking experts to collectively produce the right answer, this function encourages each expert to independently produce the complete correct answer. If expert 2 has the most correct answer, then it will be selected to represent the final output. So now the question is, why is this better? Because right now, each expert tries to mimic the entire desired output rather than a proportional of the output. And the gating network can be encouraged to route the task to the most competent experts. And the system right now becomes more selective and winners take all. In practice, this paper used negative log likelihood of Gaussian mixture model as the error function. This error function has two nice properties. First of all, it is more interpretable than the original error function. So right now, you can see this proportion to represent the Gaussian mixture model. So in this error function, the output of each expert can be seen as the mean of the Gaussian distribution. Pi here can be seen as a combination of constant and variance. So if you have 3 experts, each of them can represent an individual Gaussian. And when you have 3 experts, you can use error function to represent a mixture of 3 experts, 3 different Gaussian distribution. The other nice property of this new error function is that it has a normalization term. In the original derivative, you can see here, this is the derivative of the original function. And for the improved derivative, the difference is that now we have a weighted term. Suppose we have a very strong expert that produce nearly identical result with the desired output. So this term will be almost 0 and this term will almost be 0 too. As we iterate and do backpropagation through derivative, because we have a strong expert here, this term will be very large. And for a weaker expert in using this new derivative function, their derivative will be smaller because of this normalization term. This new improved error function will adapt to the strong experts faster than the original derivative, because if you can see here in the original derivative, even if you have a strong expert, it doesn't really penalize the weaker expert, so it takes longer to iterate using the original error function. Here is a visual representation of how we can interpret the error function as mixture of Gaussian. As you can see, we can have 3 experts and they each represent its own Gaussian distribution. We also have gating network that assign the probability of this Gaussian distribution. So distribution 1 is our P1 probability and P2, P3 probability accordingly. The combined mixture of Gaussian is a weighted sum of all the experts' output. So now let's talk about how to make competitive learning associative. Traditional competitive network doesn't really take consideration of input. So what it really learns is about the distribution of the data. And then it has a generator to generate the output based on what it knows about the distribution of the data. A concrete example you can think about is k-means. When you are using k-means, what you are learning is not a function that converts input to output, but rather you are learning the distribution of the underlying data and then generate based on the distribution. Another thing about traditional competitive network to highlight is that it doesn't consider input. And the input is exactly what this paper is bringing back in. In the MOE network, both experts and the gating network, they consider as input. So each expert's prediction as well as the probability from the gating network They are all output from the input. Now, as you can see, the competitive network in MOE is still competitive, one winner dominates, but it is also associative because the mapping depends on the input. Practically, this means that a single MOE can own an end-to-end task while letting experts focusing on sub-regions. This way, we have a powerful hybrid, a system that maintains the specialization benefits of competition, but still functioning as an input-to-output mapper. To recap, this paper introduced two ideas that connects associative learning and competitive learning. The benefits of this is that first, modularity. Each expert interfere with each other less, and they can iterate relatively independent, while at the same time, it maintains the other benefits of MOE in terms of efficiency and scalability. Scalability because when you're training, you can use all the experts, but at the inference time, you can pick only a few experts, thus saving the inference time. For efficiency, we just talk about how using the improved error function is able to have the model adapt to the strongest expert faster. Lastly, it's about interpretability because we now can interpret the error function as a mixture of Gaussian where each expert having its own distribution. Lastly, I want to talk about the analogy here. Make associative learning competitive and make competitive learning associative. Not only can they be applied to models, they can also be applied to our life. Make associative learning competitive means that you try to produce the output individually and try to mimic the desired output. To do so, you need system thinking because you need to know every component. And make competitive learning associative means that you want to collaborate and be associative. In the context of life and career, this means that you want to be part of the whole system. In order to do that, you need to specialize and be able to communicate and network so that the system will route the work to you. That's it for today. Thank you for watching.